Well, thank you for the introduction, and good afternoon, everybody. Thank you for joining. Today, I will cover a range of topics to consider when planning a modernization to communication-based train control. The typical upgrade is from a conventional signaling system or older train protection technology, usually fixed block, to CBTC moving block. An example of that would be the upcoming upgrade of corridors for Western Railway and Central Railway in Mumbai. But you also have to keep in mind that some of this is also applicable to the upgrade of older communication-based train control systems to newer generation of CBTCs. And that's the type of project that we are bound to see more and more, given the lifespan of a modern signaling system of about 20 years, and the first CBTC having been deployed in the early 2000s. So to begin with, where does CBTC fit within the range of modern control systems available to urban transit? So on the left-hand side, you have the computer-aided dispatch automatic vehicle location systems. And these are the system of choice for tramways driven on site at low speed, often mixed with road traffic. That's the same CAD-AVL technology for buses. It's very cost-effective, but more and more in a railway environment, we see some automatic train protection functions being included in the CAD-AVL. On the right-hand side, you have ERTMS, European Rail Traffic Management System, and that's a de facto standard today for train control on intercity lines, on freight lines, on the national rail networks, right? It's been adopted to some extent by Indian Railways, also on suburban lines, the Delhi Meerut regional rail transit system comes to mind, right? ERTMS for urban transit might actually be a good choice for the kind of lower capacity lines, definitely below 20 trains per hour. Might be more cost effective than communication-based train control in some configurations. Thinking of a suburban commuter lines, for example. And then in the middle, you have CBTC. Main advantages, moving block principles to allow for high frequency operations, running trains very close to one another, automatic train operation function that will allow for precision stops at stations and close adherence to a schedule or constant headway operations. And finally, third, let's say, well-proven capability for driverless trains. Now, from a procurement standpoint, the issue is CAD-AVLs and CBTC is that they are very proprietary. Basically, you're married to a single train control supplier, which means that for future line extensions or new fleets, you will have to negotiate with just one supplier. There's no competition. I'd say in the US, there's another option, which is positive train control, and it's in principle interoperable. But in practice, there are three systems mostly incompatible with one another and a very limited number of suppliers as well. So the exception in terms of interoperability is European Rail Traffic Management System, right? The big advantage of ERTMS is that you can have a choice of suppliers. Onboard equipment from one supplier will work with the wayside equipment supplied by another. You can see why some commuter lines and airport links, they don't need high frequency operations, and they would choose to go with ERTMS. The issue with ERTMS is that today the automatic train operation function on top of ERTMS is not yet standardized. So if you need ATO on your line, you're kind of out of luck for interoperability options. Now, there are efforts around the world to develop interoperable CBTC system. And this is mostly driven by two very large operators with line and fleets that were designed from the start to be operated as a single network, like Paris and New York. So Paris RATP, they chose an approach that doesn't offer complete interoperability, but it offers a choice of two suppliers for wayside equipment and onboard equipment. And then you have New York City Transit. They did something more ambitious, and they defined a fully interoperable system, and they qualified 3 different suppliers. So any of the 3 onboard equipment supplier can run on any of the 3 wayside suppliers' equipment. You have China as well. There's just so many CBTC projects, so many mass transit projects over there that it's worth the effort trying to standardize. And there's some initiatives in this direction. And for the same reason in India, there are some interoperability efforts led by TMRC with some, let's say, early successes on the automatic train supervision system. Now I'm going to explore some questions around architecture. And this is another consideration when you are kind of designing or choosing a CBTC system, is your choice of architecture. First, signaling systems used to be very distributed along the tracks, right? But with the progress of communication networks and more power available, it is now possible to centralize the signaling functions. You used to have, one interlocking computer at every station. Now it's possible to have a single interlocking computer that controls the entire line. There are trade-offs, though. Sure, but with less equipment, you have less failures and less maintenance to carry out, right? But a failure then will tend to have a much larger geographic impact. Another question of architecture is, and another example of innovative architecture for CBTC is a shift to having more of the computing done on the train, okay? Smarter train, if you will. And that means that if you do the computing on the train, you don't need to do as much on the wayside. You don't need so many computing platforms on the wayside. And with less equipment on the wayside, you have less interfaces, and with less interfaces comes faster response times. With faster response time, you can achieve shorter headways. You have better preemption mechanism for the resources, whether they are switches, to improve your headways. Alstom, as a supplier, has a couple of projects that follow this kind of new train-centric architecture. Some suppliers are also considering moving most of the computing to the cloud, even the carbon computers. After all, now again, we can have high availability, high capacity, low latency networks, both wired and wireless. So moving to the cloud means there's no need for air-conditioned signaling equipment rooms every couple of miles to house your train control servers. So kind of simplifies the overall architecture. I'd say it's still too early to see entire CBTC systems running on the cloud, but we'll get there. Already you have ABB, the Austrian railways. They run cloud-based interlocking systems for the network supplied by Siemens and Thales. So before we think of moving to the cloud, a key consideration with CBTC, and it's in the name, is communications, in particular, train to wayside communications. And there's been a lot of progress in radio technologies over the last 20 years. Most projects use some kind of Wi-Fi now, not necessarily standardized because of the need for switching quickly between access points. I mean, train moving sometimes very fast. There's also some good results with LTE. In China, especially a number of metro systems are using LTE for their train control carrier. And then, of course, 5G coming up is worth exploring. But beyond the technology is another interesting system architecture question. Should you have a dedicated radio for CBTC only, or should you have a radio infrastructure that offers vehicle to infrastructure, train to wayside communication services to more than just the CBTC application? I want to spend a little bit of time talking about train location systems, because one of the principles of CBTC is for the train to know exactly where it is and to learn about the precise position of other trains. So for this reason, train positioning is a critical subsystem. So far, the signaling industry has been very conservative, and most systems are using tachometers that are recalibrated with transponders on the track. But with price drops and an increased performance of newer technologies, and I'm talking about inertial measurement units, accelerometer, gyroscopes, LiDAR, vision systems, ultra-wideband radios, satellite positioning. These newer technologies make positioning solutions increasingly interesting. Improving localizations will allow you to run trains closer to one another, sometimes very close, right? If you have a high availability, safe positioning of the trains, you could run trains in a virtual coupling mode just meters from each other. Another advantage is reducing equipment to install and maintain, okay? And I'll go into that later. And the third advantage is fitting CBTC to more rail vehicles, including the yellow fleet, the maintenance vehicles, with smaller onboard equipment, smaller onboard sensors that are better fitted to smaller vehicles. Here's one initiative with the New York MTA and New York City Transit. They are choosing to use ultra-wideband radios instead of track transponders, and to use inertial measurement units instead of the traditional wheel sensors. So how does UWB ultra-wideband radio ranging works? UWB radios, they give you a precise distance between the radio on the train and the radios installed on the walls of the tunnel. And from that information, the train can triangulate its exact position in real time. And that's kind of a terrestrial GPS system. So why is New York doing this? It's mostly because of ease of installation. They are modernizing their signaling systems. It is a brownfield project in a subway that operates 24/7. There's no stopping of operation for track access. And retrofitting such a localization system, UWB plus inertial measurement units on vehicles, it is much easier than installing the transponder antennas on the frame or mounting tachos on axles. Instead, the system, the positioning system, is just a small box that you install behind the fiberglass front cover of the train. There's no external equipment. Now, one key issue with CBTC is that if you choose not to deploy conventional train detection systems, whether track circuits or axle counters, you need to know where the head of the train is at all time, head or tail of the train. All vehicles inserted in the CBTC traffic, they need to be equipped with CBTC, and we need to be able to guarantee the integrity of the consist. We can't be leaving a work wagon undetected on the tracks. So that's not a problem when you're equipping modern electrical multiple units, right? They come with built-in systems to make sure they're whole. But for other types of vehicles, maintenance trains, consist integrity is actually a very challenging problem to solve. There are various methods and options. For example, many properties, unequipped wagons, they are protected by 2 CBTC equipped locomotives at each end, right? Unless you can get your CBTC supplier to provide some kind of removable end of train device. One great characteristic of communication-based train control is that it's much easier to overlay on top of a conventional signaling system. And this is also the reason why CBTC has become the technology of choice for signaling upgrades. For example, train detection. You can overlay axle counters on top of track circuits. They can coexist quite well. Then you have the legacy transponder and RFID transponders. So instead of fighting for space on the track bed and on the vehicle, you go with UWB. There's no conflict. They can coexist for the duration of the resignaling project. Wheel sensors. Arguably, they could be reused, but for performance reasons, let's say you want better positioning, you can install inertial measurement units instead. No interface with the wheel sensors. And then you can still have your original speed codes transmitted through the legacy track circuits while your CBTC communication is run on a new Wi-Fi system. So by allowing you to kind of overlay the new signaling, the new CBTC system on top of the old one, you can run both at the same time. And that way you can test the robustness of the train-to-wayside communication over several months. And for example, if you need to adjust the location of antennas to optimize coverage, you can do so. Now, the most important thing when considering a CBTC resignaling is your migration strategy. And here you have basically 2 main options. The first one is dual equipping both wayside infrastructure and trains. Okay. And that's the kind of CBTC overlay I was talking about. That allows you for switching between one train control system and the other. You can build up some confidence with the CBTC by running in shadow mode. And when confident, you switch to CBTC. First, at night, during engineering hours for testing, you give control to the CBTC. If things don't work out, you have the option to revert to the old system. A second approach is to dual equip only the infrastructure and instead interface the 2 signaling systems so that the CBTC can function in a legacy ADC mode. This approach has the advantage of not requiring dual equipping the trains, and dual equipping the train can be a problem. Maybe it's a space problem. Maybe it takes a long time to do it. So by not dual equipping the train, you can have a fleet using the legacy on board, and another fleet using the new CBTC on board. This is much more complex because you need the CBTC suppliers to be able to interface with the legacy ATP, right? Legacy automatic train protection. But if you have a brand new fleet ready to be delivered and you don't want the hassle of installing the old ATP on it, that could be an interesting option. So here's an example of option one, the full switch, when combining the CBTC upgrade with a line extension. You can dual equip the train first, then you deploy CBTC on the extension, you switch your onboard signaling depending on the section of where you are, and finally you overlay CBTC on the existing line. And now that second example, this time of the alternative approach, which is mixed operation. And again, this is very useful for when you procure a new fleet in parallel to the CBTC upgrade and you don't want to fit the legacy ATP on the new fleet. Now, one great opportunity with a train control upgrade is to increase the level of automation. Nowadays, there are many fully automated metro systems. The technology is proven, the performance very high. Here in India, Delhi Line 7 and 8 have driverless capabilities. Bangalore Yellow Line is under construction. These are all good examples. Now, keep in mind there is more to automation than just upgrading the train control system, right? There's a lot of intricate interfaces with other systems, and you might need to upgrade your running stock, communication systems, or your power supply to make it compatible from a rail systems point of view with automation. Another example is that you might need to install platform screen doors to prevent track intrusion if you don't have them already. But there are very successful examples of brownfield metro lines being converted to driverless operation, and that can bring a lot of benefits to the transit agencies, right? Here's a kind of a list of upcoming projects that I know of, especially in Europe, to convert legacy line to driverless operations. So in summary, there's a lot to consider when planning a brownfield resignaling project, right? CBTCs are inherently complex systems. Greenfield projects are already difficult sometimes, but brownfields are especially challenging. And this time we're bound to see more and more brownfield projects. But in spite of this complexity, there are plenty of resignaling projects that are well managed and turn out well. With that, I thank you for your attention, and don't hesitate to reach out to me about your train control upgrade plans. I'll be happy to discuss and take questions. Thank you.